students. In this lecture, we are going to discuss about the inductance calculation for a three-phase transmission line with asymmetrical spacing with transposition. Okay, three-phase transmission line with transposed asymmetrical spacing. Okay, so as we discussed in the previous lecture, that is inductance calculation for a three-phase transmission line with asymmetrical spacing. We are using three phase conductors, phase A, phase B, and phase C conductors, right? Which are displaced by a distances like D1 be the distance between conductor A and B. Similarly, let D1 be the distance between conductor A and B, and let D2 be assumed as a distance between the conductor B and C, and D3 be assumed as a distance between the conductor C and A. Okay, these are the three-phase asymmetrical spacing configuration. So, in the previous lecture, we have calculated the inductances of conductor A, conductor B, and conductor C itself, right? So, in this, if you observe in these equations, so the inductance value of phase A, phase B, phase C, that is LA, LB, LC are three values will be unequal values. That is, there are unidentical values in the case of asymmetrical spacing. But most of the practical systems we are using a asymmetrical spacing only. But since that without in the asymmetrical spacing, all the three-phase inductances having a three different values, right? Which is not a considerable case. So to meet the balance of these three-phase inductances, that is LA, LB, LC, to meet the balance between the LA, LB, LC, so we have to introduce a transposition concept. Okay, transposition concept. So what is transposition means? So in here, there is a three positions. We taken this one, this is the position of the first position 1 of the conductor, and this is the position 2 of the conductor, and this is the position 3 of the conductor. So what in the transposition, what we have changed is that so each phase will occupy all the three positions. That is, conductor phase A will be occupies conductor 1 position as well as conductor 2 position as well as the conductor 3 position in the entire transmission line length. So in each position, each phase conductor in each position occupies about 1/3 of the total transmission line length. Okay. So let me draw this diagram. For example, there are the three-phase transmission lines consisting position 1, this is the position 1, this is the position 2, and this is the position 3. So initially, this is the starting of the line. So the entire length of the transmission line is subcategorized into three parts. Okay, three parts exactly equal and be taken as L by 3 length. Okay, L by 3 length. This is the first section. Section 1. Section 1. Again, in the second section also, and third section, so total transmission line. Okay. I am subcategorized these three transmission lines will be subcategorized into three sections. Okay, section 1, section 2, and section 3. So here also the length of the section 2 is L by 3 and the length of the section 3 is also L by 3, where L is the total length of the transmission line. Okay, this is the position 1 conductor, position 2 conductor, conductor 3 position. So in transposition, for example, conductor position in section 1, conductor A occupies position 1, conductor B occupies position 2, whereas conductor C occupies the position C. So what we are here changing is that at these two intervals, that is the intersection of this section 1 and 2 as well as the intersection of section 2 and 3. So initially the conductor occupies the position 1. Now the conductor will occupies the position 2. Okay, this is the position 2. Now the conductor A will occupies the position 2 in the section 2. Likewise, in the section 3, the conductor occupies the position 3. Likewise, In this manner, each conductor will occupy all the three positions. That is position 1 in section 1, position 2 in section 2, likewise position 3 in section 3. Likewise, we are arranging to meet the equal inductance of a individual phases. And similarly, the conductor B occupies position 2 in section 1, whereas conductor B occupies the position 3 in section 2, whereas conductor B, phase B, occupies position 1 in section 3. In similar manner, conductor phase C occupies position 3 in section 1, whereas which occupies position 1 in section 2, which occupies position 2 in section 3. So this is the called as transposition of lines. Okay, so in this manner we are transposing each and every phase into a 3 different sections. So we have to take in the total entire transmission line can be divided into 3 subcategories, and each section will be having a 1/3 of the total length of the transmission line. So in this each and every section, the conductor phase here occupies every position in each and every sections. So this is the transposition. So by using this transposition, we can meet the inductance will be taken as in all the phase conductance will be making as a symmetrical value. Okay. So now let us calculate how the inductance of each phase conductor will be calculated. So let me start with this case. Now I have to calculate. So here first I have to calculate the flux linkage of conductor A, right, in section 1. Flux linkage of conductor A in section 1. Okay, so in this section, what is the diagram? Conductor A, this is the same position we are using. Now I have to calculate the flux linkage. Let lambda A1 be assumed as a flux linkage of conductor A in position 1, which is equivalent to, you know that formula, 2 into 10 power minus 7 into the flux linkage due to its own current. That assume that for calculating this one, calculating these flux linkages, that is assuming currents, conductor A carries a conductor current IA, whereas conductor B carries a conductor IB, whereas conductor C carries a current IC. In such a way that sum of these 3 currents, IA plus IB plus IC, is equivalent to 0. Okay. Sum of the 3 phase currents is assumed as a 0. IA plus IB plus IC equivalent to 0. Now we have to calculate this flux linkage of conductor A with respect in position 1 with respect to position 1. That is lambda A1 equivalent to 2 into 10 power minus 7 into flux linkage due to its own current, that is IA into logarithm of here the position 1. So 1 by D11 plus flux linkage due to current IB, phase current IB into logarithm of 1 by the distance between B to A, that is D, that is a position 1 to, plus IC into logarithm of the distance between phase A and phase C, that is D13. Okay. Now I have to substitute the values. Lambda A1 equivalent to 2 into 10 power minus 7. Okay. In this IA into logarithm of what is D11? D11 is nothing but distance of this conductor 1 to the conductor 1 itself, that is itself radius R dash, plus IB into logarithm of what is D12, that is distance between conductor 1 and conductor 2 is assumed as D1, that is 1 by D1, plus IC into logarithm of what is the distance between D1, distance between conductor 1 and conductor 3, that is conductor 1 and conductor 3 is assumed as the D3, so logarithm of 1 by D3. So let it be taken as equation number 1. Okay. Now similarly we can calculate flux linkage of, similarly we can calculate, this is the flux linkage of conductor A with respect to the position 1. So similarly I have to calculate flux linkage of conductor A in with respect to section 2. That is flux linkage of conductor A in section 2. We can calculate this value as like lambda A2 we assumed as the flux linkage of conductor A in section 2. Okay. So for this is the configuration, right? From this configuration I have to draw the same diagram. What we have having is conductor 1, conductor 2 and conductor 3. The respective conductors are same. Here the distance between conductor 1 and 2 is same as this D1, conductor 2 and 3 is same as D2 and conductor 1 and 3 is D3. Okay, and take the same configuration, but what here is position 1 occupies conductor 1 position is, this is the C. Okay, here this one is conductor A and this one is conductor B. Okay, this is the positions. Now we have to calculate this section 2. This is the configuration of these three phase conductors, conductor A, conductor B, conductor C in section 2. Okay. Now we have to calculate this flux linkage. That is lambda A2 equivalent to 2 into 10 power minus 7 into IA into logarithm of this flux linkage of phase A current. So here phase A current is at conductor 2, right? So here the distance, own distance D2 to plus flux linkage due to phase B current. Okay, that is position 3 to position 2. That is IB into logarithm of 1 by D 3 to plus flux linkage due to phase C current. That is IC into logarithm of distance 1 and conductor 1 and conductor 2. Distance between conductor 1 and conductor 2. Okay, clear? Now I have to substitute the values. Now here lambda A2 equivalent to 2 into 10 power minus 7 into IA into logarithm of 1 by D2 is not, D22 is nothing but its own conductor radius, that is 1 by R dash plus IB into, what is the distance between position 3 and 2? Position 3 and 2 is D2. Now here 1 by D2 plus IC into logarithm of D1, that is position between conductor 1 and conductor 3 is I am assuming as D1, 1 by D1. So let it be taken as equation number 2. Okay, this is the flux linkage of conductor A in section 2. It's given as lambda A2 equivalent to 2 into 10 power minus 7 into IA logarithm of 1 by R dash plus IB 1 by D2 plus IC into logarithm of 1 by D1. Now we can calculate the flux linkage of we have to calculate similarly flux linkage of conductor A in section 3. Okay. Now in section 3. So if you observe in this transposition section 3, the conductor 1 occupies the phase B. Okay, from this one, the conductor position 1 occupies phase B, whereas position 2 occupies phase C, whereas position 3 occupies phase A. Okay, so this conductor carries IA, this conductor carries IB, whereas this conductor carries IC. Okay, now we have to calculate flux linkage of same conductor A, that is position conductor A in this section. Now we have to calculate that lambda A3 be the flux linkages in this section 3. We can calculate as 2 into 10 power minus 7 into IA into logarithm of, here phase A current is occupies in third conductor, erupting 1 by D33 plus phase due to phase B flux linkage due to phase B current, that is IB into logarithm of, here phase B current is occupies position 1, so distance between position 1 and position 3. So I have taken logarithm of 1 by D13 plus due to phase C current, that is IC into logarithm of the distance is 1 by D. Here C is occupies position 2, so from position 2 to position 3 I have taken D23. Okay, now we have to substitute the values in this expression. So lambda is equivalent to 2 into 10 power minus 7 into IA into logarithm of this 1 by D33. So 1 by D33 is nothing but self distance, that is R dash plus IB into logarithm of 1 by D13, that is distance between 1 and 3 is where assumed as D3 plus IC into logarithm of 1 by D23, that is distance between 2 and 3 were assumed as D2. Okay, that will be taken as equation 3. So this is the flux linkage of conductor A with respect to the section 3. Okay, now we have to calculate entire flux linkage, total flux linkage. So here the flux linkage of conductor A having one value in whether it is existing in section 1, it is having another value that is existing in section 2, and it is having another value which indicates in section equation 3, whereas in the position 3, that is section 3. So we need to calculate the, I have assumed all the flux linkages of conductor A in all these 3 positions are different value. So now I have to take the average of these flux linkages to get the, since that I am assuming individual flux, each and every transmission line occupies the L by 3 value. So I have taken the total flux linkage of conductor A is assumed as the average of these 3 flux linkages in respect to positions. Okay. Now we have to calculate the flux linkage of now we have taken flux linkage of phase A conductor is given as lambda A equivalent to average value of the 3 flux linkages due to all these positions, that is lambda A1 plus lambda A2 plus lambda A3 by 3. Okay, this is the average value. So we can substitute the values of lambda A1, lambda A2 and lambda A3 from the equation 1, equation 2 and equation 3. I have taken 1 by 3 into, in the all the equations, if you observe all the equations of lambda, equation 1, equation 2 and equation 3, that is the factor 2 into 10 power minus 7 is common factor. Okay, now I have substitute the values of lambda A1 from equation 1, that is IA into logarithm of 1 by R dash, okay, plus IB into logarithm of 1 by D1 plus IC into logarithm of 1 by D3. Okay, this is the equation for lambda A1. Similarly, for equation of lambda A2, we will get IA into logarithm of 1 by R dash plus IB into logarithm of 1 by D2 plus IC into logarithm of 1 by D1. Okay, these are the terms for lambda A2. Now I have to substitute the lambda A3 values from equation 3. This one is IA into logarithm of 1 by R dash plus IB into logarithm of 1 by D3 plus IC into logarithm of 1 by this section D3, this one is D2. Right? So this is the total flux linkage of phase A conductor. Now, if you observe this case here, this is 2 into 10 power minus 7 into 1 by 3. Okay, so in this terms, the first term IA logarithm of 1 by 3, here IA into logarithm 1 by 3, here IA into 1 by logarithm 1 by. Okay. If you observe these terms, IA into logarithm 1 by 3, the fourth term IA logarithm 1 by R, IA into 1 by logarithm 1 by R. If you observe from this case, what we have is IA into, we can write this one as 3 into IA into logarithm of 1 by R dash, right? 3 equations. Plus, so if you observe the next terms, here from this term IB into logarithm of 1 by D1, from this term IC into logarithm of 1 by D1. So from these two terms, I have taken logarithm of 1 by D1 as common factor, will get IB plus IC. Okay? From these two terms, 1 by logarithm of 1 by D1 is taken common factor, so the result is IB plus IC. Similarly, if you observe this fifth term, that is IB into logarithm of 1 by D2, and here IC into logarithm of 1 by D2. So from these two terms, we will get logarithm of, if you take a logarithm of 1 by D2 as common factor, we will take IB plus IC. Okay. Similarly, from this term, IC into 1 by logarithm 1 by D3 and IB into logarithm 1 by D3. So logarithm of 1 by D3 as common factor, this is IB plus IC. Okay. IC plus IB. So this is the resultant value. But from this expression, what we conclude is, from this expression, initially we assume that sum of the three phase currents is 0. So from this, IB plus IC equivalent to minus IA. So if you replace this value with minus IA, similarly in this also you can replace minus IA, and here also you can write minus IA. So now here we can replace from this IB plus IA, IC equivalent to minus IA. So in this second term, third term and fourth term, we have replaced this IB plus IC equivalent to minus IA. So from this all these terms, IA minus IA will be taken as a common factor. Now this equation becomes lambda equivalent to 2 into 10 power minus 3, so 2 into 10 power minus 7 into 1 by 3 into 3 into IA into logarithm 1 by R dash. So from these three terms, second, third and fourth term, I have taken minus IA as a common factor. Now here logarithm of 1 by D1 plus from this term logarithm of 1 by D2 plus logarithm of 1 by D3. Okay. So if you observe in this case, the bracket of this term log A in this form of log A plus log B plus log C, that is log A by ABC. So from this we can return this expression as lambda equivalent to 2 into 10 power minus 7 into, we have converting this 1 by 3 into, shifting this into brackets. So 3 and 3 gets cancel each other for this term. So this term IA into logarithm of 1 by R dash minus 1 by 3 into IA into, so I am using the concept log A plus log B plus log C here. So the resultant is logarithm of 1 by D1, D2 and D3. Okay. So this one is lambda equivalent to 2 into 10 power minus 7 IA into logarithm of 1 by R dash minus 1 by 3 IA into logarithm of 1 by D1, D2, D3. Now, so this term in this 1 by 3 can be shifted into inside the logarithm. So the resultant value will be lambda equivalent to 2 into 10 power minus 7 into IA logarithm of 1 by R dash minus IA into logarithm. So here 1 by 3 can be shifted into logarithm, it becomes root value. So 1 by cube root of d1, d2, d3. Okay. Now here in this both the terms, IA is taken as a common factor, and here log A minus log B notation. I am using this concept. Now finally, lambda equivalent to 2 into 10 power minus 7 IA into logarithm of cube root of d1, d2, d3 by r dash. Okay. So this is the value of flux linkage of conductor A, that is lambda equivalent to 2 into 10 power minus 7 into IA into logarithm of cube root of d1, d2, d3 by r dash. Okay, where r dash is the radius, fictitious radius of each conductor. So from that we can calculate the inductance of phase A conductor is given as, we can get LA is equal to the ratio of flux linkage of conductor A to the current flowing through the conductor A. It is lambda A by IA. Now substitute the lambda A value from this equation. Let it be taken as equation number 4. From this equation 4, it is 2 into 10 power minus 7 into IA into logarithm of cube root of d1, d2, d3 by r dash divided by IA. So here IA gets cancelled. So the finally LA is given as 2 into 10 power minus 7 into logarithm of cube root of d1, d2, d3 by r dash. Okay. So this is the resultant inductance of a phase A conductor. We taken as equation 5. Okay. This is the inductance of a phase A conductor as 2 into 10 power minus 7 into logarithm of cube root of d1, d2, d3 by r dash, where here d1, d2, d3 are the distances between the conductor AB, conductor BC and conductor CA, whereas r dash is the fictitious radius of the each conductor. If you derive this is the derivation for phase A conductor. Similarly, we can obtain, if you derive the inductance for the phase B and phase C also, similarly we can obtain this LB also, LC will obtain as same value, is 2 into 10 power minus 7 logarithm of cube root of d1, d2, d3 by r dash. The units are Henry per meter. Okay. So if you derive this is the derivation for phase A conductor. Similarly, if you derive for the phase B as well as the phase C, we will obtain the same value as equation number 5. So the finally, the inductance of three-phase asymmetrical conductor can be obtained as by using this formula. Okay, by using this formula, 2 into 10 power minus 7 logarithm of cube root of d1, d2, d3 by r dash Henry per meter. Okay. Now we move on to the problematic part on this asymmetrical spacing with transposition of a three-phase transmission line. Now we are going to discuss about some problematic on asymmetrical spacing with transposition three-phase transmission line. Now read out this question. The question is given as a transmission line has conductor diameter of 1.8 cm each. Okay, the conductors being spaced as DAB equivalent to 4 meters, DBC equal 9 meters, and DC equal to 6 meters. Okay, the loads are balanced and the line is transposed. So find the inductance of the line per kilometer per phase. Okay, so this diagram, we start this three-phase asymmetrical transposed line having a phase A conductor, phase B and phase C conductor. So here they are given that radius of diameter of each conductor is given as 1.8 cm. Okay, each conductor having a diameter of 1.8 cm. And the distance between A and B conductors, we are using A, B and C conductors. Distance between A and B is given as 4 meters and distance between B and C is given as 9 meters, and distance between C and A is given as 6 meters. Okay, so this is the configuration. Now we have taken the what is the given data. So the given data is given as DAB is given as 4 meters, DBC is given as 9 meters, and DCA is given as 6 meters. Okay. From that we have to calculate D equivalent is equivalent to U root of D1 into D2 into D3, that is equivalent to U root of D1 is under DAB into D2 is distance between B and C into distance between D3 is distance between C and A. Now substitute these values. D equivalent to U root of DAB is 4 into DBC is 9 into 6. Okay, if you calculate this value, we will get the D equivalent to 6 meters. Okay. Now they are given as diameter of each conductor is 1.8 cm. So from that, the effective radius virtual radius R dash is given as 0.7788 times the R. Right? Here R is nothing but 0.7788. Distance diameter by 2, that is 1.8 cm by 2, but here cm is written in cm, have to convert into meters, 10 power minus 2. So if you multiply this value, if you substitute this value in calculator, you will get about this value is 0.701 into 10 power minus 2 meter. So this is the R dash. Now we have to, this is the R dash, 0.701 into 10 power minus 2 meter. Now we have to calculate inductance of the line. Inductance of the line is, you know that from the formula, this is 2 into 10 power minus 7 into logarithm of D equivalent by, that is cube root, D equivalent is nothing but cube root of D1, D2, D3 by R dash. Now substituting the value, 2 into 10 power minus 7 into logarithm of D equivalent we obtained as 6 meters by R dash we obtained as 0.701 into 10 power minus 2. If you use the calculator, you will get this answer as, this is the per phase inductance, L per phase, okay, one phase inductance, which is obtained as 113.5 into 10 power minus 7, okay, and the units are Henry per meter. So this is the phase inductance of the transmission obtained as 13.5 into 10 power minus 7 Henry per meter. But they are asking for inductance per kilometer. So we need to, we obtained this inductance value, per phase inductance value per meter. So we need to multiply 1000 factor with this equation to get the per kilometer length. So inductance per phase equivalent to 13.5 into 10 power minus 7 into, I have to multiply the 1000. Okay. So the resultant value will be taken as 13.5 or 1.35 into 10 power minus 3 Henry per kilometer. Okay. Here 10 power minus 3 into Henry get as millihenry. Therefore, the inductance of the line per phase obtained as 1.35 millihenry per kilometer. Okay. The inductance of the line per kilometer per phase is obtained as 1.35 millihenry. Okay, this is the problem. Thank you.